Okay, we are going to continue with volumes, but we're going to take a little bit of a time out with volumes of revolution.
Wait, are these easier?
Yes. These are volumes by cross sections. What's a cross section? Okay, you take a lemon and you slice it up, and you have cross sections that are circles, right? Or circular. Lemon's not always perfect. Okay. So what we are going to have is an area where we have shapes laying either perpendicular to the x-axis or perpendicular to the y-axis, where their cross-section is a geometric shape. Yes?
Did you make that take that picture?
I wish.
I was about to
I
say,
wish.
that's really impressive.
Wait, so, because those seem like they're at a diagonal, are they going to be like that, or are they?
They're not at a diagonal. The picture's taken at a diagonal.
So they're all the same height.
The yellow should.
Yeah.
The yellow should.
Like it gets bigger.
Okay, so these are, okay, so what these are like, these are rectangles where maybe the height is related somehow to the base, okay?
Oh yeah.
So like these are semicircles. So obviously these semicircles are going to be taller than these semicircles, right? These squares are going to be taller here than they are here because their width is different. Okay? So they're not all the same height, right?
So it's not like a shape on top, it keeps the same shape all the way up.
Right. Okay. Now, how might we find the volume of something like this?
You would have to find the, like,
third
geometric area of the shape and then include it into it.
Okay. How do we find, like if I had this right here. This is a square, but then it's 3D. Okay, so it's a cube, right? How do we find the volume of something like this? Not a cube, but a rectangular prism. Okay, we find the area, and then we times it by the height, and now we have volume, right? Okay, so if I can find the area of these, how thick are they? Okay.
No, dx.
These are thickness dx, right?
Because they're vertical.
So can we add up all of these areas? And how would we do that? Okay, so we're going to take an integral.
It's like the little rectangles, but now it's 3D.
Okay, so if we have cross-sectional area in a plane perpendicular to the x-axis, here's our cross-sectional area that we're going to sum up from A to B with thickness dx. We're adding up all of these infinitely thin cross-sections.
So it looks like a bugle with those expanding the other way.
Sure.
So the ones that are up there, those are in respect to the x.
Right. Now, what if our cross-sections were with respect to the y-axis?
It'd be like the other way.
Okay, then we'd have to integrate with respect to y. Okay. Did you write this down?
Yeah.
Okay. A volume of a cross-section, we're going to integrate the areas with thickness dx or thickness dy. Okay. Now, there are some pictures in your book. These give pretty nice pictures. Go ahead and turn page 426. So on I really like on 427, at the top left, they have these triangles that you can see a little bit better what the actual shape is as opposed to, you know, these paper things I have on the board. Okay, but you see we have an area in our plane, and we have a shape. In that case, those are what kind of equilateral triangles? Okay, so we have a bunch of equilateral triangles based on our area. Okay, yes.
Wait, so this isn't the cross-section of a revolution, this is just, this
No.
has nothing to do with.
It is not, that's why I said we're taking a break from revolutions.
I was confused.
Yes. Okay. All right. So what we're going to need the area where our cross sections lie, and then you will have to draw a picture of the geometric cross section. Okay. What you're going to need to know in this section is how to actually find area of geometric shapes. Can you do that?
Depends on the
Do we
shape.
have to do proofs?
Okay, so this is an example that we're going to do with different cross sections. Okay, so we want the volume of a solid whose base is bounded by y equals x plus 1 and y equals x squared minus 1, with the following cross sections perpendicular to the x-axis. So first of all, let's draw our area. Y equals x plus 1. Looks like this. Y equals x squared minus 1.
Travel, travel.
Where do they intersect at?
2, 3, 4,
2, 3. Right, because it would be 2, 4, but it's shifted down 1 for the parabola.
Also, it's negative.
Okay, and maybe 1, 0. All right. So now we want cross sections perpendicular to the x-axis. So that means we have shapes lying here. Okay, which tells us we're integrating with respect to x. Okay, and these are squares. Okay, so I'm going to draw my square, my green square that's lying here. Okay, so this right here that I'm highlighting, that is what's lying right here standing up. So I have this square sticking out of my board. Okay. What is the length of that side of the square? That's how thick
Oh,
it is.
it's the line minus the rest.
Okay. This square is lying right here. So this length would be top function
Minus bottom function.
minus our bottom function. Hold on. So what's this length?
That.
Negative x squared plus x minus 2?
Yeah.
Okay. So the area of each of my squares would be
There would be 2 there, would there? 'Cause negative 1 plus 1 is 0.
Oh, negative 1 minus 3.
No, but it's x plus 1.
I was going to say something's weird. It's x plus 1, right? So this is a plus 2. Thank you. So our area is our side squared. Okay. So to find the volume of this funky shape we've got going on, we're going to take the integral of our area. So area times thickness gives us volume. And we're going to add up all of these volumes together from -1 to 2. Pretty sweet, right? Yes.
It's negative x squared plus x plus 2. Like, at any point, that'll equal.
Yeah, anytime I have a square in here, it's lying in here, and the base of the square has length from here to here, right? And so that would be this function minus this function to get that distance, right? The lengths are determined by how far apart those two functions are. Okay? That's why we have to use calculus, right? We can't possibly find the area of every single one of them. Okay. All right. Same bounded area. Let's find the volume if our cross sections are rectangles whose height is twice the base. Okay? Same. That was a horrible drawing, but that's okay. We still have cross sections perpendicular to the x-axis. So here's my slice. Now, these are rectangles. Ooh, that worked out nicely. Here's rectangle, right? The base is always what's sitting in here. The base of our rectangle what's the base of our rectangle?
Negative x squared plus x plus 2.
Okay, because that was the top function minus the bottom function. How high are these rectangles? Twice that. So the area of each of these rectangles would be 2,
To that square.
okay, base times height, right? Okay, so the volume of each of these rectangles would be our area times our thickness, and we are going to add them together from -1 to 2. What? Now, semicircles.
So we're like, the problem like asks you to give one function, and then it asks to do multiple different shapes.
Probably not multiple different shapes, but I don't know.
Like, because we're using the same function or shape.
Well, right now I'm doing that. So I don't know what's going to be on your quiz or test as far as if you're going to get the same region with multiple shapes or a different region for each shape or for each shape. Okay. I do. Either way, we'll be able to do it, right? Okay. So we still have our cross sections perpendicular to the x-axis. Now, what's lying here and popping out of your page is a semicircle. Okay, now hold on. This represents what of the semicircle? The diameter. Okay, so our diameter is -x squared plus x plus 2. Is that what it is? Wait, yeah. Okay, So our area needs to be 1/2 pi r squared, correct? Which would be 1/2 pi
That.
times negative x squared plus x plus 2 over 2 squared. Okay. So when we set up our integral, our volume would be 1/8 pi negative x squared plus x plus 2 squared. Is everyone okay with what I just did there?
Yes.
Okay, so there's the area times the thickness added up from -1 to 2.
Because it's 1/2 square.
Because this is 2 squared, makes it a 4, times 1/2 is an 8. That just made it look prettier, doesn't matter, no. Okay, but if you were to do this by hand, you would want it to look like that first, right? You don't want to do those fractions. All right, we're good at this now. Let's look at an AP problem. Okay, so this is only a portion of one of the free response. Okay, in a free response question, you will for sure have a free response question that will ask you about area and volume. Okay, so this is a portion of the 2010 number 4 question. So we have R as a region in the first quadrant bounded by 2 radical x, y equals 6 in the y-axis. And they actually gave you the picture. That was nice of them. Region R is the base of a solid. For each y between 0 and 6, the cross-section is taken perpendicular to the y-axis, is a rectangle whose height is 3 times the length of its base. Write, but do not evaluate, an integral expression that gives the volume of the solid. So now we have cross sections that are perpendicular to the y-axis. How thick are they? Y.
Do they even need to say that the y-axis was down if it's
No. But they did. They were redundant. Okay. So now we're going to have to integrate with respect to y, aren't we? Which means I need to know what this equation is. Y squared over 4. Do we agree?
Y over 2.
So y over 2, and then we have to square that, which is y squared over 4. Okay? So now that blue represents the base of our rectangle, right? What is the base of our rectangle? Y squared over 4 minus 0. So it's just y squared minus 4, y squared over 4. Okay. Our rectangle has a height 3 times the length. So 3y squared over 4. Right? Okay. So our integral, we're summing up volumes from
0 to 6, or no, 0 to 9. 0 to 6. 0 to 6.
0 to 6.
I'll put it 3 times.
Okay. Our area would be
3y squared over 4. Over 6.
that's the thickness. Area times thickness summed up from 0 to 6. Okay. How about that? What I'd like you to do, I would take it out the door. Okay? So what you can do is you can rip out a piece of paper, tear it in half maybe, and split between 2 of you. Okay? What I want you to do is I want you to complete this problem. All right? And I want you to hand it in to me as you leave. Okay? Your homework assignment, I will write up here for you. Okay? And this ticket out the door is what you're gonna work on until you leave. Okay? So let's read it together. The base of a solid X is the region enclosed by y equals natural log x equals e, and the x-axis. Our cross sections are perpendicular to the x-axis, and they are squares, set up, just set up, to the volume. Don't integrate, please. So I should see a picture and an integral. Well, I should see two pictures, right? Two pictures and an integral. Picture of the area, picture of the shape, picture of the integral. What? Oh, what the?
I mean, is it this way?
I don't know, just forgot to check it.
I think it's exactly that way.
Function aerobics, people.
That's e to the x.
Oh,
Yeah,
It's like
this is e to the x.
Yeah.
oh, so it's yeah.
Where does it intersect the x-axis? Why do we have calculators?
Use approximately
So I can know
2.2, 2.5.
X equals E, and then E is just a value. It's just 2.72.
Okay. When x is e, what's y gonna be here?
Oh, one.
Oh, because, yes.
May consult each other. Okay, that's good.
Okay,
So
that's
x is e is gonna be where?
is it is word
Yeah, over here.
where
somewhere.
e
Yeah, so x equals e. Okay. Somewhere over there.
so it's gonna be this right there.
Yeah. So the top function is natural log of the bottom function. You have it done before the bell rings? You can finish it.
Probably not.
Don't say that. Careful. What's the area of the square? Good. Good. Okay, let's look at it. We're summing up values. Where do we start? So your integral just start at. Yeah. I know zero is kind of a fault, right?
How long does that charcoal bar last?
That's confidence, but you want to make
How do you think confidence is very?
When you take it
You
out,
should have confidence.
it's plastic, it's not
Good.
glass.
Maybe a Rex.
Good. Why are you not so long? What's the right one? That was the right one. Oh, yeah, but I really get your choices. Well, x equals u would be this way. Oh. Yeah, so it would be this area right here. Okay. Good. Okay. This is 1, right? X equals E is a vertical line over here. You drew it at 1. No, it's X equals E.
What does that look like?
What does that look like? Okay, here's your function, right? E is a little bit more than 2, right? So it's gonna be like here. So we're talking about this,
Oh,
okay? So, instead, let's just talk about it.
yeah.
Our integral would go from 1 to E, and our square has a base. Good. And so then that would be this word, yeah. Okay, good. Get it fixed?
I think so. No.
Okay, now,
From 1.
it would be from 1 to E, yeah,
Well, yeah. I
Yeah.
could do that.
yeah, good, so yeah, that's better.
Okay. Thank you.
Uh-huh.